I'm going to do my third and final mathematical concept video. And that is phi, or phi. There is some discrepancy as to how it's pronounced. Some people say phi, others say phi. And as such, I looked it up to see which was correct. And it turns out that both pronunciations work. However, it seemed that most mathematicians use phi. So I'm going to go with that pronunciation throughout the rest of my video. If you pronounce it phi and this annoys you, I'm sorry, but I had to choose one. But, pronunciation discrepancy aside, let's get on with the golden ratio. Now, phi, which is approximately 1.6180, is known as the golden ratio. Now, I'm going to explain the ratio part first, and I'll get to the golden part later. Now, for the ratio part, we are going to take a square, which will be 1 unit by 1 unit. And they're the same, of course, because, it's a square. And to that square, we're going to add a rectangle, which the longer side is 1 unit, because of how it's attached to the square. But we don't know the length of the smaller side here. Now you can see that by adding on this rectangle to the square, we have formed a larger rectangle, which goes all the way around the square and rectangle combined. And the length of the longer side of this larger rectangle, we will call x. Now, the special thing about this shape is that the ratio of the sides of the larger rectangle, so the ratio of the sides would be the 1 over x, so that's the ratio of the shorter side to the longer side. Now, the ratio of the sides of the larger rectangle is the same as the ratio of the sides of the smaller rectangle. So we'll have the longer side on bottom, and the shorter side is then 1, or x, minus 1. Because you can see, this full length is x, and this length is 1. So if we subtract 1 from x, we get this length here. That math works out, trust me. So we now have this equation, which is 1 over x equals x minus 1 over 1. Now, from this point, we can then solve for x. And the special thing about x is phi, and I'll show you how. So, we'll multiply x to both sides from down here. So we now have 1 equals x squared minus x. And we can just ignore this over 1, because anything divided by 1 is just itself. Now, we'll subtract 1 to both sides, giving us now x squared minus x minus 1 equals 0. Now, we now have a quadratic equation, which means we can use the quadratic formula. So, we'll have negative b, and since b is negative 1, so we have 1 plus or minus the square root. Let's see, we got negative 1 squared minus 4 times 1 times negative 1. All over 2 times 1. Now, I'm not really going to go through and explain the quadratic formula. I made a video about that, conveniently enough, so if you're confused about it, you can just click on this and it'll take you to it. But, nevertheless, we have our equation, so we continue solving this. So we have 1 plus or minus, let's see, negative 1 squared, that's just 1. 4 times 1 times negative 1, well, it's negative 4 times 1 times negative 1, so that's just plus 4. And that's over 2 times 1, which is just 2. Get rid of that, I don't need that extra part. So we have 1 plus or minus the square root of 5 over 2. Now, if we do 1 minus the square root of 5, we will get a negative. And since we're talking about geometry, a negative length doesn't really make sense. So we now have 1 plus the square root of 5 over 2. So this is what x equals. This is our answer to x. And if you type that into your calculator, you will notice that you get approximately 1.6180, or phi. So you get phi by using this equation. So that is how phi is a ratio. And it sets it apart from pi and e because you actually have an equation to write phi. You don't need to estimate phi. You can write an actual equation for it. Now, there is another, and this is a slightly more common ratio for phi that I'm going to mention, although it's not as easy to explain what phi is. But the other ratio, is if we have a line segment, A, and we split it up such that, so we have the longer side of the split up being B and the smaller side being C. And we have the ratio such that B over C equals A over B, and B should be phi, and C will then be 1. So you can also get that ratio using this line segment. That's another way to get the ratio, but I went with the rectangle because it's easier to explain. But nevertheless, you can see that this is phi. Alright, now, while I did mention earlier that because we have an actual, essentially an equation for phi, we don't need to approximate it. Now, just because we don't need to approximate it, doesn't mean that we haven't approximated it, because we have. Which is where Fibonacci numbers come in. Now, Fibonacci numbers probably deserve their own video. They're cool like that, but I haven't made a video about them, so I can't direct you to a more in-depth explanation of, of them. So I'll just give kind of a brief rundown now. Now, for Fibonacci numbers, it's a series, and what you do is you add the previous two terms of a series to get the next number in that series. So, we're going to start with the first two terms, which will be 1 and 2. Now, if we add 1 and 2, we get 3. Now, to figure out the fourth term, we're going to add the previous two terms, which are 2 and 3, so if we add 2 and 3, we get 5. Now, again, to get the fifth term, we add the previous two terms, which were 3 and 5, so we'll get 8. And again, continuing on, we'll get 13, and then 21, and then 34, and then 55, and then 89, and, so on. Just continuing that same pattern. So this is the Fibonacci series. These are Fibonacci numbers. Now, what's cool about them, and how they relate to phi, is if you take one of the Fibonacci numbers and divide it by the previous Fibonacci number, you will get a relatively close approximation for phi. Now, the farther on in the series you are, the more accurate approximation you get. For example, if we take 2 divided by 1, we get, 2, and that's not a very good approximation of phi. However, if we just do 13 divided by 8, we get 1.625, which is a much more accurate approximation of phi. And as you continue on farther into the series, you'll get even more accurate approximations of it. So it's just kind of a cool little thing about Fibonacci numbers. And it provides an important relationship between Fibonacci numbers and phi. So far I've covered the ratio aspect of phi, but I haven't really talked about why it's golden. So, why is it golden? Well, it doesn't show up a whole lot in math. I mean, there aren't very many mathematical equations that make use of phi, but it does show up pretty much everywhere in nature. Like, for example, take the human face. Now, I'm not a very good drawer, so these aren't going to be the best pictures, but just go with them. So, take the eye, and then the center of your face. So, from the center of your eye, then to the center of your face, using the edge of your eye as a dividing line, the ratio of this length to this length is phi. Also, we'll take your lips, the center of your lips, to then the edge of your face, using the edge of your lips as a dividing line. That ratio is also phi. And you'll notice here, we make use of the line ratios that I mentioned earlier. I told you they'd come in handy. And these are just a couple examples of phi on your face. It also shows up from like the edge of your face to the center of your closer eye to the center of your farther eye. That's a phi ratio. Also, from your eye line to just beneath your nose to just beneath your chin. That I'm pretty sure is also phi. Also, moving beyond your face, it also shows up in the human body in many places. Like, I believe the length from your shoulder to your elbow to, I think, might be the bottom of your hand or your wrist. I'm not entirely sure on that one. But I believe that is also a phi ratio. So, it just shows up many, many places on the human body. Now, it also shows up in other places aside from the human body, such as plants. And these more relate to Fibonacci numbers instead of pi directly, but of course, as I mentioned earlier, Fibonacci numbers also relate to phi. So, for example, if we cut open plants, like certain fruits, like say, for example, we cut open an apple, we'll notice that there are 5 segments, which is a Fibonacci number. Now, if we cut open a banana, we'll notice there are 3 segments, which are a Fibonacci number. Now, I'm sure this is also the case with many other fruits. If you cut them open, you'll notice they're split up into Fibonacci numbers. Feel free to cut open as several fruits and just notice them. Just be sure you eat the fruit afterwards. Don't let it go to waste. Something. Also, in plant growth, for example, say we have a plant, so it starts with one stick, like one twig, and then it splits off into 2. Then in the next stage, it might split off into 3, and then it'll split off into 5. Which you'll notice, those are all Fibonacci numbers. And in fact, after this, it'll split off into 8, and then 13, just continuing this Fibonacci series after each split. So yeah, plants relate to phi. In fact, even there's a spiral pattern you can see on certain plants. And if you count the number of spirals, you'll notice that they will make a Fibonacci number. And there are several different spiral patterns you can actually see. Like, if you look at it, you can see a certain spiral pattern, though you can also notice other spiral patterns. They're all Fibonacci numbers. Now, I don't have a plant, so I can't really show you this. So I'd encourage you to look this up yourself, either by finding an actual plant, or looking for other videos that'll show you this. I know there are some videos that'll show you this. I've watched one of them. But so yeah, I just recommend you look at that for yourself, because it's pretty cool. Now, of course, aside from the human's body and then plants, it shows up in DNA itself. Now, so DNA is kind of a double helix thing, which I think, I'm not a very good drawer, as I mentioned. I think it's kind of like that. Yeah, there we go. Now, if we go from the length of one segment of it to then the width of it, that length over width is, of course, phi. And also, you'll notice we have a minor peak and a major peak. And if we go from the edge of there to that peak, so like the peak just before the minor to the one just between the minor and the major and the one just after the major, we'll notice that this ratio here, that is, of course, and also phi. So yeah, phi shows up everywhere. And, it shows up in other animals aside from just the human. And, of course, it shows up in plants and DNA. It also shows up in art and architecture and music, which are things we make. Which, it really isn't that surprising that they show up in things we make, because since it shows up pretty much everywhere in nature, more likely than not, we have phi kind of ingrained into our brains. I'm sure we naturally think in terms of phi, and we also see phi everywhere, so that would be a large inspiration for art, architecture, and music as to why it shows up there. So that's not terribly surprising. But aside from that, it also shows up in the solar system. Like, for example, the radius of the moon and Earth, if they're put right next to each other, they'll form a triangle with the hypotenuse being phi, and even the ratio of, like, orbits and periods of rotation relate to phi for certain planets. Phi's everywhere. Now, if you ask me, this is an indication that everything's connected. Because if phi shows up in DNA, then it makes sense that everything would stem from one point, because then the phi ratio in DNA would spread through all of the creatures. So, yeah, it makes sense that it all kind of come from one place. And as for it showing up in the solar system, I'm sure, now, this is just speculation here, but there's probably some relation between phi and physics that causes, you know, the orbital periods and why it shows up in DNA. So I think nature just naturally works in terms of phi. So yeah, that was my video about phi. Now, as with my other 2 mathematical constant videos, this is of course not everything about phi, so if you're curious about it, I encourage you to look up more about it. I especially encourage you to look up more of these ratios that just show up in nature. It's just really cool to see them, so I'd encourage you to do that. But yeah, I hope you enjoyed it, hope you learned something, and see ya!